So for lesson 2, before we look at log functions and then taking the derivative of log functions, we need to understand and remember from 30-1 what an inverse function was. And how do we find an inverse function? What is an inverse function? So this example says, find the inverse of y is equal to 2x plus 6 and sketch the graphs. So first thing, let's just look at this original function here. Let's sketch this, and then we'll figure out what the inverse function will be. So y is equal to 2x plus 6. If we sketch this, this is in the form of y is equal to mx plus b already. So that means that the y-intercept of this graph is going to be at 6. So y-intercept of 6. The slope of this graph is 2 over 1, which means that you would rise 2, run 1, rise 2, 1, 1, or you would fall 2 and go to the left 1. But what I'm actually going to do in order to get this graph is we already have the y-intercept. Let's figure out what the x-intercept is. So for an x-intercept, remember we're going to let y equal 0. So for this function, I'll have 0 is equal to 2x plus 6, and we'll solve for x. Negative 6 is equal to 2x. Divide by 2, divide by 2, an x-intercept at negative 3. Okay, so this graph here, we've got the y-intercept, we have our x-intercept. It's a linear graph. If I have 2 points on my graph, I could connect those 2 points, extend the line, and I will have my graph. So the graph of the original linear function will look like this. And I'm going to write it in function notation. So I will say f of x is equal to 2x plus 6. Okay, in 30-1, we did inverse functions. And I'm going to show you how we figure out the equation of the inverse function. But inverse functions, they're functions that are going to be reflected in the line y is equal to x. So what we need to do is we need to put in our graph a hatched line that will go through y is equal to x. Now the line y is equal to x, if you remember, where the points on the line would be like, so the equation of this line is going to be y is equal to x. And y is equal to x, if you were to like create a table of values for it, when x is 1, y is 1. When x is 2, y is 2. So the points on this line would be 1, 1, 2, 2, 3, 3, 4, 4. But this graph, or this line here, is the line y is equal to x. Inverse functions, what we did was we interchanged x and y. So this point here is 0, 6. Where this point would be on the inverse graph, 0, 6 would be where? 6, 0. So the inverse of 0, 6 would be 6, 0. So this point is reflected in the line y is equal to x, and it would be here. This point here, which is negative 3, 0, would be 0, negative 3. So this point reflected in this line would be 0, negative 3. So that point would go down here. And then the other thing about inverse functions is the invariant point, so the point that's the same on both graphs, is the point that lies on the line y is equal to x. So this point right here, which we'll calculate in a minute, that's going to be an invariant point. So the inverse graph, it will go through the 3 points. Now, it's going to be slightly off because it's not to scale, but the inverse graph should be going through this point here. So maybe what I'll do is I will do this. To make that minus 3, I'll just go like that. And then there it's minus 3. Okay, this is the inverse graph. So it is f prime of x. This is going to be the inverse graph. So how do we find the equation of this red line? The original equation was y is equal to 2x plus 6. Do you remember what we do for inverse equations? You switch the x and the y. So switching the x and the y would become x is equal to 2y plus 6. So for inverse equations, we switch x and y, and then we solve for y. So if I was to solve for y, I would get x minus 6 is equal to 2y. Divide by 2, divide by 2, divide by 2. Y is equal to 1 over 2x minus 3. So the inverse function, which is this red line, it's a reflection of the original function. It's reflected in the line y is equal to x. It should have a y-intercept of 3. The slope of this red line is positive. The slope is rise of 1, run of 2. And because this is a function, it passes a vertical line test, I could rewrite this in function notation, but because it's the inverse equation, I'd write the f prime of x, and I'd say that the equation for that is 1 over 2x minus 3. Now, let's say I said to you, where do these two graphs intersect? So where does this first graph intersect with this graph? Well, where the two graphs intersect is they intersect right here, and that's the invariant point. How you would find that intersection algebraically is you're going to let y1 equal y2. So if we had our calculators, you would type this into y1, this into y2, and we'd find the intersection. Well, we don't have our calculators, but these are nice equations. So the equation for y1 was 2x plus 6. The equation for y2 is 1/2 x minus 3. Okay, you set those two equations equal to one another, and we're going to solve for x. Now, what I'm going to do is I don't want to have this fraction, so I could get rid of the fraction right away. What would I multiply both sides of the equation by to get rid of my fraction? 2. So I'm going to multiply this by 2 and this by 2, and I would get 4x minus 12 is equal to x minus 6 plus 12. Thank you. Let's bring our x's to the left-hand side. So I'll get 3x is equal to negative 18. Divide by 3, and x is equal to negative 6. So this invariant point, where the two graphs will intersect, would be negative 6, comma. Sarah, how can I figure out the y value? Plug it into one of the equations. Which equation would you plug negative 6 into to figure out the y value? Yeah, I'd probably plug it into the original as well. So f of negative 6 is 2 times negative 6 plus 6. That would give me negative 12 plus 6, which would give me negative 6. And remember, I said that invariant points will occur on the line y is equal to x. So negative 6 should make sense. Okay, so that is reviewing inverse functions. Why do we have to know inverse functions? Because a log function is an inverse of an exponential function. So let's think about this. Just at the top here, I want you to write an exponential function. Okay, so y is equal to b to the power of x. If I said to you, I want you to take the inverse of this function, you know that to take the inverse, we interchange x and y. So that would become x is equal to b to the y. And then what we do is we solve for y. We got to get y by itself. So y right now is an exponent, and that's the whole purpose of logs. If you want to get y by itself, you're going to convert this into a log. So to isolate y, we get y is equal to log. The base of the exponential function is the same base of our log function. Isolate y, the answer here becomes the argument. And then this is our log function, logarithmic. So I'll do another one of these so you could see. So essentially, if I told you to graph an exponential function and a log function, they're inverses of one another. They're going to be reflections of one another in the line y is equal to x. And we'll draw that so that you could see that in a second. Okay, so look over here and let's do the example y is equal to 7 to the power of x. That's an exponential function. It's a growth function. Y-intercept is 1. If I said to you what's the inverse of this function, you would say, okay, inverse of this function, let's interchange x and y. So x is equal to 7 to the y. That's the inverse. And then you want to always solve for y, but y is an exponent. So to get y out of being an exponent, we write it as a log. And as a log, it would be y is equal to log, same base of 7 of x. So graphically, what does this look like? If I said I want you to graph y is equal to 7 to the power of x or 2 to the power of x, let's just graph a base greater than 1. Let's graph an exponential function with a base greater than 1. So we would have a y-intercept of 1, and this would be my exponential function. So y is equal to base of b to the power of x, and this is going to be base greater than 1 because I want it to be a growth graph. If I say I want you to graph the inverse of this, well, an inverse graph, it is always going to be a graph that's reflected in the line y is equal to x. Okay? This point here, which is 0, comma 1, is going to be here now. It's going to be 1, comma 0. Now, the inverse of this graph, so remember, y is equal to b to the x. The inverse of that is x is equal to b to the y. Solve for y. Y is equal to log base b of x. So this graph here would be y is equal to log base b of x. So exponential graphs and logarithmic graphs are inverses of one another. Okay, so that's sort of the first important thing to understand. What we did in lesson 1 is we took the limits of exponential graphs. So I said to you in lesson 1, what is the limit as x approaches infinity of b to the x? So Alex, for my exponential function, as I approach infinity for the exponential, what is my limit approaching? Yes. So this limit would be approaching infinity. Then we said, okay, the limit as x approaches negative infinity of my exponential function, it's a growth graph. Curious, what would the limit be approaching if x is approaching negative infinity? 0. Now what we could do is we could look at my log graph. And I could say, okay, what is the limit as x approaches? Now I can't approach, actually I can approach infinity for my log graph. Okay, so I could approach that infinity of my exponential function, or sorry, my log function would be log base b to the x. So Shaywa, what would that answer be? It would be infinity. And for my log graph, I can't approach negative infinity. Do you know what I'd be approaching? 0 from what side? So my log graph is approaching 0 from the right or from the left? from the right. So 0 from the right of log base b of x. And Carly, what would that be? It'd be negative infinity. Now, couple things that I want you just to make note for log graphs that are really important to understand from, I don't know if you made these connections in 30-1, but we'll go through them. Exponential growth is extremely quick. So write down exponential growth is very, very quick. Conversely, log growth is incredibly slow. It will eventually get to infinity, but it is super slow, and I'll show you how slow log growth is. So conversely, logarithmic growth is very slow. Growth is very, very slow. Okay, so let's review a couple of things. Does anybody remember from 30-1 what the log of 100 is? So first thing, if I don't give you a base, it's a common log. Do you remember what the invisible base is if I don't give you the base? 10. Okay, so it's a common log if the base isn't there. You could write it in if you need to. It's a base of 10. If I ask you to evaluate the log of 100, what you are asking yourself is 10 to what power would give you 100? Do you know what the answer is? 10 to what power would give you 100? 2. Yeah, okay, let's look at this one. You guys write this one down. Log base 2 of 8. Yes, you say to yourself, 2 to what power will give you 8? 2 to the power of 3, so the answer is 8. If I said this one, log base 2, no, log base 5 of 25, what's that answer? 2. Okay, so the log of 100 is 2. Here's what this means. What this means is this is our x, right? You guys, x is right here. So what this means is when x is equal to 100, y is equal to 2. So look at how slow log growth is. When x is equal to 100, here's 1 on my graph. This is 1. When x is 100, so way over here at 100, y will finally get to 2. I'll give you another one. What is the log of 1,000? So 10 to what power will give you 1,000? 3. Okay, so what that means is on our log graph, when you finally get to x is equal to 1,000, so you got to go all the way to x is 1,000 to get to y is equal to 3. So it's just very, very slow growth is logarithmic growth. Okay. A couple of other things to write to review. Write down 2 to the power of 3 is equal to, what's 2 to the power of 3 equal to? 8. How would you write this as a log? So 2 to the power of 3 is equal to 8. So how you write this as a log base 2, yeah, the base of the exponential function, exponential equation is 2, so this is 2. What's my argument? 8 is equal to 3. And think about this. If I said evaluate log base 2 of 8, well, 2 to what power will give you 8 to the power of 3? Are you remembering all this? Okay. Flip your page and let's review some more things with logs. Write down log base 3 of 3. Same base, same argument. Do you remember what the answer is? Ask yourself, 3 to what power will give you 3? Akil? 1. Okay, so if I said log base 5 of 5, the answer is 1. Log base 7 of 7, the answer is 1. When you have the same base, same argument, you get an answer 1. Okay, we looked in 30-1. What happens when you have an argument of 1? 3 to what power will give you 1? Yes. 3 to the power of 0 will give you 1. So if you have an argument of 1, we'll have 0. 3 to the power of 0 will give you 1. Okay. What will this be? Same base, same argument. 1. Now, how are we going to do things in calculus? We're going to introduce e. E is a number, a rational number, 2.71. So log base 2.71 to the power of 2.7, or argument 2.71, what's the answer? 1. Okay, so don't panic when you start seeing e's everywhere. Okay, let's review the power law. So this law right here is the power law. So if you have, write down log base 2 to the power of 4. There's two ways that you could do this. You could evaluate what 2 to the power of 4 is. And then, so what is 2 to the power of 4? What is it? 16. So here's one way you could do it, which I wouldn't recommend. Log base 2 to the 16. And then 2 to what power will give you 16? What's that answer going to be? 4. Now, the reason why I don't recommend doing this way is because if I give you something like log base 2 to the 10, we don't want to know what 2 to the power of 10 is. So what we could do is we could employ the power law. So we could take this exponent and we could make it the coefficient of the log. So the 4 will go in front. So it becomes 4 times log base 2 of 2. Then, when you see the same base and the same argument, that answer is always 1. 2 to the power of 1 will give you 2. So that will give us 4 times 1, which is equal to 4. The reason why we want to use the power law whenever we can is for something like this. I don't want to figure out what 2 to the power of 10 is. So I want to bring the 10 in front, and it will be equal to 10 times log base 2 to the power of 2. Log, same base, same argument, is 1. So this answer would be 10. Okay. Do you remember? Write down 5 log base 5 of 25. So first of all, before you see what the pattern is, evaluate what the log base 5 of 25 is. Yes, you say to yourself, 5 to what power will give you 25? So that answers 2. So the evaluation of log base 5 of 25, this is 2. Does that make sense? Like this log is equal to 2. And then 5 squared is 25. Now there's a shortcut that you could take. Does anybody know what the shortcut is? If you have a base raised to a log of the same base, what will the answer always be? The argument. So here's where I could make it more complicated. I could say 3 raised to log base 3 of 96. And you'll say, I don't know 3 to what power gives me 90, like what that is. So base of 3 raised to log base of 3, it is equal to the argument. The answer for this will be 96. Okay, so you want to be able to see that. Okay, so the next thing that's going to be new is something called natural logs. So in Math 30, we did common logs. So those were logs that were so common the base was 10, right? So here was the common log, log of 100. This is a common log, okay? So common log, the base isn't written, it's a common log, it will be 10. Then you would say, okay, 10 to what power would give you 100? So that answer is 2. So the log of 100, the evaluation is 2. What we're going to do is a log that has a base of e. So e, remember, it's just an irrational number, and e is approximately equal to 2.71828, goes on and on forever. So what we're going to do is we're going to look at logs with this base. Now, before we do that, if I said to you, I want you to graph y is equal to e to the x. So we've sort of done this, right? Y is equal to e to the x. That's an exponential graph. The base is 2.71, so it's greater than 1. It's a growth graph. This would be the graph of y is equal to e to the x. Then, if I want you to graph the inverse of it, we're reflecting in the line y is equal to x. So that's the line y is equal to x. This point here, 0, 1, becomes 1, 0. It goes here. What's the equation of this line? Well, to figure out the equation, you're going to interchange x and y. So y is equal to e to the x becomes x is equal to e to the y. Then what you're going to do is you're going to isolate y. So you're going to write this as a log. So y is equal to log base e of x. So this graph here is y is equal to log base e of x. Now what we've done in math is any log that has a base of e, we're going to give it a new notation, and it's going to be called a natural log. So if we have a log with base of e, it's a natural log. So the notation for this, log base e of x, the other way that I could write this, which is how you're going to see it, you're not going to see any more log base e. You're going to see y is equal to, how we write natural logs is ln of x. So argument here is x, argument here is x. ln is the notation for natural log, and it's just telling you that it's a natural log with a base of e. Until you get used to this ln notation, we'll write log base e. But eventually, you'll do it so often, you'll be comfortable not writing ln of e, and you're going to write natural log of x. Okay, so what do I mean? What is this? So students look at this at first. This is the first time you see natural logs, and they panic, and they're like, I don't know what that is, right? So ln is a natural log at the base of e. The argument is this guy, which is e to the x. Now, if I said to you log base e of e, what is that going to equal? What's log base e of e? It's eventually going to be 1, but we have to employ the power law first. So where am I going to move this x? You're going to move this x to the front, and you're going to get x times log base e of e. Same base, same argument is 1. So we're going to have x times 1, which means the natural log of e to the x is x. That's the answer. Okay, this one here, e raised to the ln of x. So at first you're going to be like, I have no idea. Like, she just told me what e is. I'm trying to figure out natural logs. So we're going to write this. That's our natural log. So my base is e. Natural log of x is log base e, argument of x. So I've got a base of e raised to a log base of e. What was the answer? X. The answer is the argument. Okay. Does anybody know what the ln of e is going to be equal to? It's going to be equal to 1. Now, until you see that, like when you get good, you're just going to say ln of e is equal to 1. Natural log of e is equal to 1. But ln of e is the log base e. It's the natural log. Here's the argument of e. Log base e, argument e, same base, same argument. You get an answer of 1. Okay. ln of 1, do you guys know what this answer is going to be? It is going to be 0. And again, ln is a log base e. The argument is 1. Whenever you have an argument of 1, e to what power? E is 2.71. To the power of 0 will give you 1. Okay, sorry, this should be 0. E to the power of 0 will give you 1. Okay, so the only question you're doing is these type of ln natural log questions with base e. So it's question 3 on page 375. F I do want you to do after we finish part 2. You need to do log laws, which is in, I'll do the second part of this lesson. We'll do log laws, which will be tomorrow. And then tomorrow we'll be doing derivatives. Let me see. Lesson 3 will be the derivatives of logs. So this is just figuring out natural logs, base E.